Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast. My guest today is Marc Miskin. We're going to talk about he's at University of Pennsylvania, first of all. He's an assistant professor in electrical and systems engineering. He's working on some nano machines, and we're going to talk about, creating swarms of, very small robots that can explore, us, maybe explore other beings. But Marc will describe it. So thanks for coming, Marc. How you doing?
Good. How are you?
Good. Yeah. So tell me about what your research is about.
Yeah, so we're interested in building tiny robots, as you said. So particularly microscopic ones that are so small that you can't see them by eye. And the basic vision of how we're trying to do it is we're trying to take the technologies that were developed by the semiconductor industry over the last 50 years and start to apply them to the task of robotics. So everyone knows we can make smaller, cheaper, faster computers, and we want to bootstrap off of that to start building the smarts of tiny robotic machines.
What scale on average?
Yeah, so the typical size of the robots we build are about 10 to 100 microns in size. So a micron, micron's about 1% of a hair's width. So each of these robots falls between a tenth to a hair's width, and it's total size. It's actually just about a hair's width is a nice number because it's just about the smallest thing you can see by eye. So they're right under the line for that.
Yeah, I thought a hair is about, 75 microns?
Yeah, obviously depends on the person, right? But yeah, that's about right for the ballpark, about 75 to 100 microns.
At these scales that you're talking about, from what I've learned just of basic physics, I guess the frictions, the shears, all the physical forces on them will be different. Is that happening a lot at this scale? Or
yeah,
if you go smaller, then, the game changes again? Like what happens at this scale you're working at?
Those are great questions. Yes, so absolutely. So there are kind of two big jumps that take place as you get smaller. Three if you go really small. But the first one is the jump you're talking about. So as you get tinier, things like friction and adhesion, like how sticky you are relative to a surface, how viscous a fluid is, they become all of the dominant effects instead of things like mass and inertia and things like that. And so the consequence of that is you wind up in this world where everything is over damped. Like if you stop applying forces, you don't keep going, you have no inertia, you just stop immediately. And everything is kind of sticky, that if you come along to a surface, right, there's all these forces trying to pull you down into the surface. And they're all really big. And the reason's really simple, right? The things I just described to you, things like friction, adhesion, viscous drag, they're all properties that tend to scale in proportion to the area of an object. Whereas things like inertia and gravity and weight all scale in proportion to the volume. So as you get really small, your area to volume ratio gets really, really big. So that becomes the world that sort of takes over. And it has really weird consequences. One is the obvious one that just in describing it to you, imagine everything in your universe is like flypaper, right? Everything's super sticky. And when you put your foot down, it's not totally clear you're going to be able to pull it back up. But on the other hand, you don't have any weight, right? It's not hard to move yourself around.
The energy expenditure of one of these machines must be a lot, especially for its size. So I'm sure that's a challenge.
No,
it's constantly being dampened, right?
That's true, but it also swings the other way that while you're correct to point out that you have no way of storing energy in your motion, right? So you can't run like a cheetah where you're bounding and storing energy and kinetic and potential energy. And you're right, every step you take is just dissipative, right? So it just gets lost into heat. On the other hand, your size is so small that the actual forces are really, really low. So to run around, if you're a 10 micron robot, it only really takes about 12 piconewtons. And the total energy you burn, it's a fraction, it's nanowatts. The numbers are so small that compared to doing a task like, say, computing or sensing, it's in the noise. It's basically negligible. So it swings both ways, right? All of your energy is lost, right? It's totally dissipative. But on the other hand, you're not really losing all that much.
But what about, for nanowatt or nanovolt, I don't know how it correlates, but for very small voltage differences, I would think those would arise anytime you're in a biological system, just naturally. And would that zap the device or interfere with it?
Yeah, I mean, the robot's insulated, right? So it's got its internal body and its external body. To be clear, like the voltages that are like in between cells and things like that are much bigger. They're usually on the order of like microvolts, so 1,000 times bigger than a nanovolt. When we scale down in size, right? You scale down all of the mechanical aspects, like the forces and stuff like that, but the electrical aspects you can kind of keep the same. So when you talk about things like computing, as we make it tinier and tinier, at least the first approximation, kind of the characteristic voltages and currents are actually still fixed, which is kind of cool, right? So you don't have to worry too much about electrical interference for these little guys. They kind of work. They're happy.
What were some of the other challenges you were talking about?
Oh, in terms of being small?
Yeah.
Yeah. So, but yeah, you brought up a really good one, right? So the drag and adhesion, and like that's a really big one. Just to point out too, right? Like that's why you can't use like gears or like just shrink down a motor, because all the gears and parts get stuck. It doesn't work. So you have to rethink a lot of those things. One of the other really weird consequences too, by the way, is that the way that you have to move in order to like swim or propel yourself becomes very different. Because as we're sort of talking about it, right? Like if I can't rely on inertia, the fact that the mass keeps moving when I get it in motion, then a lot of strategies like the way you or I swim or like big animals swim or run, they just don't work. So you have to rethink a lot of the basic aspects of robot locomotion when you get small, just purely based on that fact.
Are you having to do a lot of biomimicry, making flagellas, for instance, or similar, the analog in a robot?
Yeah. So we do that for sure. So we have a project that's going right now where we are building little nano flagellas and like nano cilia and stuff like that. I mean, they're micro, right? So they're big. They're not quite like nanoscale, although they are made of materials that are nanometers thick. And yeah, for sure, like the inspiration there is biology. In fact, it turns out that like if you compare, a flagella has a specific, like a certain stiffness to it. So like how much force does it push back on you if you push on it? It turns out that the stuff we build is actually comparable. It's almost the same value, just kind of neat. So you can just kind of steal a lot of what biologists have discovered and start thinking about it for strategies for your robot. On the other hand, we do stuff that's also totally not biomimicry. So, we are playing with a different toolkit. We're talking about silicon and wires and metal, and that gives us access to some things that biology just can't do, right? That there's not a lot of microorganisms that have access to like loads of platinum or crystalline silicon. And so we do come up with some other strategies that are totally, there's no equivalent in biology, but we're able to play around with it just because we have this different set of rules.
Yeah, but then if you're using it in biological applications, what about the biotoxicity of these things that aren't normally there?
Yeah, so to be clear, right, the biotoxicity of platinum, for example, is kind of low. We do work on that. The idea is that everything that's on the surface of our robots, if it's in a biomedical application, is made out of a material that's called generally recognized as safe. So, we have been making implantable electronics for 30, 40 years now, and there's a lot of data that you have on what's toxic and what isn't. And so what we do is, the complex things that go on the interior of the robot are encased, or isolated from the external environment, and everything that's on the outside of it is in one of these material classes, that it's low toxicity, that it's not poisonous, and that there's a good history of showing that.
Well, since the feature size is so small, you'd have to be very careful with, I guess, the material science, surface science, so you don't have rough surfaces, because anything even somewhat rough on that size would probably totally confound what the machine does, or, adhere to everything in 2 seconds.
Yeah, no, for sure. I mean, that's the magic. In some ways, that's like one of the most amazing triumphs of all of semiconductor fabrication, is that there's a toolkit that lets you go after that stuff, right? But you're totally correct, right? So the wafer you build on is more or less atomically flat. The processing that you have to do is, like the legs of this robot are 7 nanometers thick. They're just a dozen atoms in size. And so you're totally right. If you start messing around with what that surface looks like, what's on it, like any one atom adsorbed on the growth surface prior to doing it can have big impacts. But somewhat remarkably, there's a toolkit to do that, right? That been making electronics now tinier and better for 50 years. And there's just this huge body of knowledge that you can draw on to go after those things. But for sure, it's a huge consideration. Absolutely right.
What other forces have you haven't mentioned that are very important? Is that enough to do, on the scale you're working?
Oh,
You talked about drag, dampened effects, etc. What other forces are highly present that you need to worry about?
this is kind of cool. I'm glad that this is like a super mechanical discussion, right? So it's normally like we're off in a different space. I always want to talk about the mechanics, but nobody asks me. So I'm just so you know, I'm having fun with this.
Well, good. Good.
Yeah, and actually a really good question. So I teach a class on this, and like this is pretty close to the first two lectures. So we're like, you're right on the money, man. Yeah, the big forces that you care about. The third one that we haven't talked about is elasticity, right? So when I talk about the robot's legs and it's like running around, something actually has to overcome drag and all of these other forces. And so that means you need both legs that can bend and deflect in order to cause motion. And then you need some mechanism of creating forces to cause that to happen, right? So the robot's got to control something to move its legs. Elasticity turns out to be a pretty big one if you design the parts right. Like you can build stuff that's relatively stiff compared to, say, adhesive forces or drag or whatever. And part of that engineering is what determines like whether your flagella is going to work or whether your leg is going to work. So we tune that. The trickier one is figuring out how do you actually make the forces in the first place. And in fact, this is kind of the key innovation that in some ways of what we did. If you want to build a robot, right, you have to both make a force that's going to move this thing around. And that force also has to be controllable by the electronics, right? It's not enough to just make forces. Like I got to be able to turn them on and off. And those are two pretty big constraints, right? Because you have to create enough force in a tiny size over a very small area, right, to build your little tiny robot leg. And it has to be controlled by a signal that's about, going to play nice with the silicon electronics, which has a very specific voltage range. It's about 1 volt. And so we came up with this way of doing that. We call them surface electrochemical actuators. But the idea is pretty simple. It's you make a very thin layer of platinum, and you put it in water, and you apply a voltage to the platinum relative to the water. And when you do that, atoms from the water will attach themselves to the surface of the platinum depending on how much voltage you use. That creates a force at that surface, right? Because you've now changed the number of atoms that are there. And it turns out that force is actually quite large. It's big enough to do a lot of actuation when you're small. The other nice thing about this approach is that the voltage that it takes to go from, say, like no atoms on the surface to the surface is totally covered is about 0.2 volts. So it's right in the sweet spot for what you want it for plugging these things into pieces of electronics.
So when atoms bind to a surface, are they, I guess, electrostatically deforming it? Because now the topology of I guess their electron clouds is what's deforming the material, or is it just physically they're displacing some of the materials on a surface?
So it's closer, I think, to the first thing you said. So the idea is you can view it like they're chemically bonded, right? So if you're a chemist, you could just say, well, they form a bond with the surface. And when they do that, they change the bond density. Physically, though, what that means is what you're describing, right? Is you've changed the charge distribution at the surface, and that's going to alter the forces that are present there. That's not changing the charge distribution, is moving the electrons around. In point of fact, like it's a little more complicated than just normal electrostatics because you're talking about electrons. But the rough intuition is not so far off there.
And I guess because you're not yet doing stuff with the nanoscale, you're avoiding some other issues. I would think like charge density and distribution would be much more important at the nanoscale, and you're getting more quantum mechanical effects too.
Yeah, it's interesting. We tend not to see very much, even for these guys so like that leg where you're attaching the atoms to, it's 7 nanometers thick, right? So its cross section is roughly nanometers in size, but it really does behave otherwise like pretty much like a bulk sheet of platinum. And yeah, you're right that the part of that is that the other dimensions of this thing are very big, and so it tends to average out. But yeah, if we were to make it much, much tinier, for sure things would be way more complicated. Like, for example, if the robot was smaller by a factor of, if it was a micron instead of 10 microns, collisions from the water molecules would start to diffuse it around, right? It would start moving randomly, just because it'd be tiny enough that those little forces from the solvent around it banging on it would have an impact. And then getting even smaller as you get down to the nano size, right? You'd really have to worry about all kinds of new physics.
So what kind of applications are you, considering for these nano machines? And also, I haven't even talked to you about the communication between them and amongst them, but let's talk about applications first.
Yeah, I mean, this is still proof of concept. So I think the long-term vision, like the 10-year out vision, is we'd love to see these in kind of we'll call them biomedical applications, I guess, where you really want something with single cell precision.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
So, if you've got this robot and it's roughly the same, it's 10 microns, it's roughly the same size as a lot of cells. And we're starting to look towards whether or not there are places where that makes sense, where that can be useful. And so, one place is kind of in say the nervous system where, it's an example, right? In the nervous system where whether a nerve exists or not is whether you have motor function. So that's something where you really want single cell precision, where if you could say, attach to nerves and record what they're doing or help perform surgeries, things like that, that could potentially be game changing. But of course, right, we're way in the proof of concept phase. So we're building robots and we're happy to show that they can walk. It's still going to be quite a long time before we can do, I think, something significantly useful.
Well, when you get to that point, what do you think is going to be the entry method? Is it going to be through syringe, if it's going to go into a person? Or is it going to be like incision and implantation? I guess I know it's early, but when it comes to that point, have you thought about how it'll be done?
Yeah, so I think it would depend very strongly on the application. I think if you were trying to build something where, just as an example, right, let's say you want to build something that's going to go into a specific nerve conduit, right, then you probably want to do that by implantation. If you want to send it into, say, a region to monitor, then probably injection is a more reasonable solution. I think it would depend enormously on what you're trying to do. Although it's probably worth pointing out that all of those things would be on the table, right? That these little things are small enough, they fit through the tiniest hypodermic needle you can buy. So in some sense, right, there's very few ways that you can interact with them that you couldn't, you can interact with them basically as though they're a chemical, right? That you pick them up, we've sucked them up in pipettes, injected them back out, they're fine. And based on that, there's a lot of flexibility in that deployment mode.
I guess they could be, at some point aerosolized and inhaled or, put onto the inside of a Band-Aid and maybe integrate that way, et cetera.
Yeah, as long as you can demonstrate it's safe, right? That's the key. So,
right, yeah.
But you're correct. The physical dimensions are such that those kinds of things are possible. And in fact, we had a complementary project by one of my colleagues at Cornell who was building just sensors, so not robots, but they're the same size roughly, and they can get data. And he showed, you can aerosolize these things and spray paint them onto stuff. So you could spray paint sensors on an object. You can inject them into resin molds and then cure it into building, a sensor into that structure. Once you get it down to that size, it's a chemical. And so, yeah, exactly. You could put it in battery, cloth, whatever you want to do, as long as it's safe and it's reasonable.
Well, if you keep going down in size, though, at some point, when it comes to biological systems, you'll be able to go in between and around cellular structures, and you may not even be beholden to, I guess things can become too mobile. It's actually maybe good that you're operating at this size because, once you put the robots in a certain place, they'll kind of tend to stay and they have inertia to stay in the same place and not travel too far. And if they were too small, then any force, any diffusion gradient, anything would carry them to places maybe they shouldn't go, is what I'm saying.
Yeah, no, absolutely. There's a related, you raise a very good point, right? That if they were any smaller, you would have a lot of weird effects that would randomize stuff. I often think about is that why cells are the size that they are, right? Biology picked a pretty specific range for sizes of cells. They're about 1 to 100 microns. And in some sense, right, maybe that's part of that puzzle, is that if they were any smaller, there'd be all kinds of other weird stuff that would make it a lot harder for cells to organize and work together. So yeah, it's a great point that maybe you don't want to go any smaller, maybe there's a reason for that goes beyond even just our engineering.
How important is it going to be for centralized control of a swarm? I'll just call it a swarm versus interswarm communication and feedback. So if you have 1,000 robots in an area, essentially they can do micro sensing and they can give you real granular details on some aspect, pressure, temperature, whatever it is. And if they communicate with each other, they can take action in a different way than just being centrally controlled.
Correct. Again, a really great question. I think my perspective is there are two schools of thought that bring their own benefits, right? So do you want to build the robot overlord that tells every robot what to do and monitors everything? Or do you want all the behavior to be more like biology, like it's emergent, that the robots communicate locally and play by their own rules, and then they do something useful by virtue of their coordination? We're exploring both, so we're really excited by the fact that we have a system that lets us kind of play in both of those spheres, as well as things that are in between. But yeah, my gut feeling is like I think it's, again, super application or dependent, like on what you're really trying to pull off. My vibe is that the decentralized one is robust. Like it's, as you're pointing out, right? Like if there's no central controller, then I can kill 30% of the robots and it's still going to figure out a way to organize itself into something useful. Whereas the centralized controller frees up a lot of flexibility in terms of, like, tiny robots do still have limitations in their memory and what they can store and how well they can process data. And you can alleviate some of that by offloading it onto, some other external framework. But that's also going to constrain your applications. It's a great point, though, right? That there's these two totally orthogonal ways of doing it. I don't think we really know yet. Still trying to figure that out, which one's ideal for what.
Yeah, and also, continue along the lines of like a bee colony. You have different kinds of bees, workers, drones, queen, etc. Within a swarm of robots to do a job, it may be good if certain ones are better at cutting, certain ones are just more mobile in a different way, certain ones are better at anchoring, different roles for the swarm, depending on the application.
Totally. And also, it doesn't even have to be that the bodies are physically different, right? That a swarm can have like multiple different components within it that are still communicating and working together. And so that's something else we think about, are like ways to build, the fun part, right, is so that everything's made with this technology for microelectronics manufacturing. And so one of the neat features of that is that complexity is basically free. If you want to build, a wafer that has 1 million robots on it, that's about as easy as making a wafer with 1 million different robots on it. It's equally, you can make as many specializations as you want. And so one of kind of the fun things for us from just like a robotics point of view is that, like, normally if I want to build 60 different kinds of robots and I'm going to build 1 million of each, right? That's a tall order for your grad student, for anybody. But with this platform, you can really start to explore those kinds of ideas, and that's really exciting.
So you're going to go with, can you even do 3D printing of this scale, or is it like chemical vapor deposition, or how do you build the bodies of these things?
Right. So one, you can do 3D printing. We don't do it, but you can. It's just nuts, but true. So yeah, a lot of it is it's most of the robot is built with like classic semiconductor stuff, right? So we have a silicon wafer, we dope the wafer with dopants, we metallize little metal contacts by physical vapor deposition, as you're saying, just bread and butter semiconductor stuff. The only part that's like maybe kind of edgy, which at this point isn't even really, is to make their legs, you have this part that's 7 nanometers thick. And that's a pretty tight tolerance, right? Just a handful of atoms. We use a technique called atomic layer deposition. So the way that works is you have 2 chemical reactions that you do in series, like A, B. And as you do each of those, that's called one cycle. And each cycle basically puts down a single layer of atoms. So that's probably the most interesting technology involved in the fabrication. But the rest of it is, normal semiconductor stuff.
Okay. Are any of these going to have payloads, chemical payloads or other kind of payloads that they'll leave on site as they work?
So we'll see. So one of the things I've been trying to figure out if we can do it, is to build little robots that do electrochemistry, like do electroplating. So the idea is like, if you work it out, it looks like it should work, right? You can get enough energy in there, and we already have them doing electrochemistry to move the leg, so it's maybe not a stretch. But the concept is similar. It's kind of what you're describing. So the robot would like run around, and then it could plate metal to like act as a payload to deliver that to a specific location. And then by coordinating their behavior, right, they could plate up some structure to build some geometry you want, or change a structure around so that it has some specific material properties. And then when they're done with that, they can reverse the reactions and then plate the metal back into solution and free themselves. So we've been thinking a little bit about stuff like that. We've also been thinking about stuff where like just more classic payloads, like they just carry things. One of the cool things about these robots is that their load to carry, like the amount they can carry relative to their body weight It's about 20, so they can carry about 20 times more than they weigh. So it's pretty much on par with like an ant. An ant is somewhere between like 10 and 50, depending on the ant. So we've been thinking about stuff like that, like, you see like these pictures of like ants carrying giant leaves. Like in principle, the little robots can do stuff like that. So, could you build them where they push around like blocks of material to build something useful?
So you said you're still like in the proof of concept phase. What have you been able to create, and what environment are you trying to test it in right now?
Yeah, very little. So very proof of concept. Like where we are is we've demonstrated, a flag in the ground is we've demonstrated that you can integrate the legs with electronics, right? So we built a very simple proof of concept robot that had very rudimentary circuitry on it. So basically some solar cells hooked up to wires, and then those were wired into its legs. And that robot walks. That's all it knows how to do is you fire light at the solar cells that causes the legs to move, and off it goes running around. Now, we built 1 million of these, right? So we did demonstrate the aspects of scalability and massively parallel fabrication. And really what that robot shows is that while we did a very simple circuit, the process we used to build it can generalize to arbitrary pieces of silicon electronics. And so, the proof of concept, you always do the simplest thing that demonstrates the idea. So that's what we built. And now what we're trying to do is move to the next phase where we actually build complex pieces of electronics. So where we are now, we're designing things where there's, sensing, programmability, where there's an internal control system for the robot to change its behavior. And all of that lives on the electronic side. And then we're going to use the same process that we developed in the proof of concept phase to attach legs to it, deploy it, and release these things. And so that's kind of the step, right? Is what we've kind of shown is like, yeah, this is doable. It's possible. And all these doors are opened up. And now we're about, third to halfway through taking the next major step of genuinely building something programmable, intelligent, and some level of information processing.
Yeah, I can see there's a lot of disciplines that have to come together to do this. And I guess like you're saying, there's still a long future ahead of it. I know, just for fun thinking, what's like a really audacious goal that you think would be possible in the next 5 or 10 years with these micro machines?
So a really ambitious goal that would be possible. And can we set the timeline a little further in the future? So I want to get my students. Well,
let's do it 2 ways. Let's do 5 years and let's do 20. What things do you think are possible given those 2 time horizons?
I think in and you want a goal as in an application or like a technical milestone?
Well, either, yeah. What do you think, just in general, what do you think is going to be possible?
So I think in a 5 to 10 year time frame, it would be very feasible to have a microscopic robot that is fully programmable, that you can write instructions to, that costs less than a penny, and can be programmed and talk to your cell phone. I think that's a feasible near-term goal in a 5 to 10 year timeline. That sounds cool. Great. And I think going further than that, in the further out timeline, I would hope that there would be applications. And so, in let's say a 20 to 30 year timeline, I would genuinely hope that we've been able to demonstrate that these things are safe for use in vivo, and that there's where we're capable of using them in thing like single cell medicine or something like that.
Okay. Well, very good. Marc, what's the best way for people to get in touch with you or, to follow your research and see what's going on?
Sure. They can get in touch with me via my email address, which is posted on the Penn website. And of course, they can keep track of what our group is up to. Again, we have a website at cs.upenn.edu/twiddle-and-miskin.
We'll have to write that down for the show notes. Yeah. Great. All right. Well, very good. Well, Marc, thanks for coming on the podcast. I really appreciate it.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.